For our next talk, I'd like to welcome Rick Gerber to go ahead. I'll just advance this to the next that one. Oh, here we go. There you go, Rick.
Thank you. Afternoon, everybody. As you were just told, my name's Rick Gerber. I'm a hydrogeologist with an entity known as the Oak Ridges Moraine Groundwater Program, which is basically 15 government agencies, 5 regional levels of government, or municipal level of government, and 10 conservation authorities. Ranging the 5 municipalities of the City of Toronto, Region of Halton, Peel, York, and Durham, and then the 10 conservation authorities that occur within that jurisdiction. So our study area is basically South Central Ontario. And this program has been functioning since 2001. So today, I kind of want to tell a bit of a story, I guess. The story is a mountain of data, in this case, groundwater level data. And the question is, what does it all mean? The answer is, I don't really know yet. But the idea is, let's try and systematically look at all of this information. I mean, it's collected by the province, conservation authorities, municipalities, our group, sometimes consultants loan data to us or provide data. So there's all this information, and I don't think it's really been given a great shake. So we've embarked on an adventure, I guess, to try and systematically start looking at all this information and try and get as much out of it as we can. And I guess in the last slide, there was a number of co-authors. I should shout out particularly Mason Marchildon, who's here. He puts together a lot of these analysis tools that come out of conversations. So it's a lot of his work and blood, sweat, and tears in this. But basically, to look at what we hope to get out of all this groundwater level data, and I'm talking for the most part, right now we're analyzing logger data, but of course the manuals are important too, especially when you look at weird things that go on that can go on in a groundwater level hydrograph. One of the key things is manual water levels to check things, but so a few of the things that we can hopefully apply this to is for our study area, we generate maps like a water table map or a potentiometric surface map. And usually that's taking a whole load of locations, taking an average groundwater level, and these locations measure in different seasons, different years, whatever. So when you bring all that together and interpret it and render it up, it's almost, perhaps let's think of it as an average condition. So then the next question would be, well, what can we expect seasonally as a variation from that average condition? Other ways that we can utilize these data are to help us hone in on numerical model calibration targets. What is the range? It may or may not be plus or minus 10%. And then as far as another utilization of it is how does our basin, how do our watersheds behave? What are the dynamics? How do they respond to pumping? How do they respond to climate change? And then also, I like to use a lot of these data for to help me figure out geology, because you can never have enough boreholes or cored boreholes, or cored boreholes, but you can always get a lot of information that would help with that interpretation from groundwater levels. So I'll go through, we'll start with the physical setting. I'll basically show you the key geologic characteristics of that area, of our study area. The data and methodology, I'll show you that briefly. At the end of this, I'll point you to our website where a lot of the details you can get at. And then we'll look at some of the results. So I guess to me, this is an exercise in kind of pattern recognition, I guess. Can we recognize patterns? Can we compare sites with similar and or different patterns, and ultimately why? So borrowing some OGS products here, we have a bedrock topography on the top, and the brown with snow capping on top are the high areas over the shield, and to the west, the Niagara Escarpment. And the bottom panel, the deep blue, means we've filled in that bedrock valley with a succession, a quaternary succession over, say, the last 135,000 years of glacial and interglacial sediments. So for the most part, about 135,000 years ago, we sometimes preserved hills on top of bedrock. Then we've got, say, 80,000 years of more lacustrine conditions or glacial lacustrine conditions. And we also have sediment supply coming off the adjacent uplands. So the shield, the escarpment. So we're going to get like a fluvial inputs to this. So often, like a lot of our great aquifers are gravel in channels. And that would be the extent of those and hydraulic properties, et cetera, is more of a proximal distal relationship to those sediment supply zones coming off the upland areas. And this is a north-south cross-section. Basically, that light green NT is the Newmarket till. This is the 20,000-year-old till from the last glacial maximum. And above it in orange, we have a major aquifer system like the Oak Ridges Moraine, which is kind of an elevated reservoir sitting on that till. And then beneath that till, we have the lower sediments, or that package of, say, 80,000 years of glacial lacustrine / glacial fluvial material. Those C1s and 2s, we think there's a couple different generations of channels running through the system. The C1 would be all in the lower sediments, still preserving that protective aquitard up top, the Newmarket till. We also have later channels, approximately 14,000 years ago, where we think we've cut through in some places that Newmarket till. And for the most part, the moraine forms a divide all the way down through and to bedrock. So looking at the data that we have, we, meaning a number of different actors, municipal governments, the PGMN, the Provincial Groundwater Monitoring Network, which is the province in partnership with conservation authorities. We collect data, consultants collect data. There's a ton of data. And you can see the locations on the left, and on the graph, it's basically, what are the numbers there? There's probably a handful, let's say less than 15 locations that have about a 30-year record. For the most part, we're looking at most of the locations have like a 10 to 15-year record. So the methodology we have chosen is in the top left panel. We're looking at a hydrograph, and we're boiling it down to daily data, daily averages. So for the most part, we have hourly logger data, sometimes more frequently than that, but basically this is all based on daily averages. So in the top left is a hydrograph, and you can see a trend. And it just so happens, John, is that that trend is rising until about 2010, and I think that kind of jives nicely with some of your figures that we just looked at. So on the bottom left panel, we're detrending that data, taking that trend off, and then in the right, we're analyzing the detrended fluctuation in daily groundwater levels. And we're using a generalized additive model, which basically breaks that annual hydrograph up into 12 segments and finds smoothing spline, they call them knots, to put together a trend. And that trend is isolated on the bottom. Those are meters, so we're looking at plus or minus, say, 0.4 meters as a range, as an estimated seasonal range for this location. And And then the long-term trends are longer than seasonal. We're analyzing with just a man Kendall. Like, are there trends and are they statistically significant? So we've turned this into interactive maps. And in this case, what we're looking at is seasonal variations first. And you can see on the left, we've got locations, and these are all locations where the screen is less than 20 meters deep. And you can see that the size, well, you can't see that, but the size of the circle is related to the range that we see seasonally in the hydrograph. And you can see that there's some pretty big ranges, like greater than 5 meters for some, and for others, less than a meter. But it's quite variable. So it's not like on the moraine, we have a range of whatever. On the till plains adjacent, we have a range of. It's not that simple. But basically, you can get into, you can play around with the map, and you can also then kick out and have a look at the time series hydrograph with estimated precip and well, not estimated, but observed precipitation and estimated snowmelt on top of that. And for the most part, and this is not a statistical analysis, this is me kind of with what's left upstairs looking at 700. So basically, we've done an analysis where there's we wanted more than 4 years of data. And for the seasonal analysis, there seems to be 3 major patterns. One is the typical in the upper left, where the groundwater peaks seasonally in the spring. The low is late fall, September, October. Below that, you can see that the low, the annual low, is kind of pulled into the summer. And a lot of times that is often because we have pumping nearby, or for some of the bedrock wells in the northeast quadrant. Some of those wells have that pattern too. And on the right, so those 2 types on the left are basically 80% of our data, or of the data, what they show. And on the right, you can see where we have peaks that are in the summer or late summer. That vertical line is July. And this is due to a number of different things. Some is dewatering for roadways, so it's anthropogenic. A lot of these locations are on the moraine proper, on top, so it's uplands, perhaps related to deep water table conditions. A lot of it is what's called bad data, I guess, where there's a lot of gaps or jumps in the data. So the key is to look at the hydrograph to see what the statistics are telling you, because it just could be bad data. So we do have, you know, we can summarize seasonal variation. And we can do this a number of different ways. Here, I'm just breaking it down by formation. We're looking at about, in the deep system beneath that Newmarket Till, seems to have more of a variability, like up to 3 meters per year. And a lot of that is just driven by the fact that a lot of our municipal systems come from the deep aquifer system, and that's affecting the range that comes out as a seasonal range. The shallow subsystem, we're looking at a range of a little over a meter in general, but you can see there's a lot of play in that depending on where you are. And then we can also look at long-term trends. And this is, again, you can go to an interactive map. And if you look at the left, like triangles facing up are where we see increases. Triangles facing down are where we see decreases over the last, and these trends are for the last 10 years. The key, one of the things, the key about trying to figure out trends is you're not going to, if you have a 20-year record, chances are in our humid climate, you're not going to see a 20-year monotonic change like that. That rise up to 2010, now we're looking at a gradual decline in many locations since 2010. So it's not a monotonic exercise. I'll show an example of that in a minute. But again, here you can look at areas where you are. Do you see any trends? And the black dots are where there's no trend. So just as a summary then, all of the data seasonally, we're looking at a range of about plus or minus 0.6 meters. Again, I would suggest to people go to the map to look at your area specifically to see what other wells in that area are showing. And again, the longer term trends, it depends where you are. There are some areas that are declining, some areas that are increasing, and some areas that don't have trend at all, long-term trend. And then, so this is, I call it the Rick Gerber with a crayon and a light table kind of phase, and it's me saying, well, what can we add to this? Like, we're just scratching the surface, and I thought I'd like to really overlay a lot of these trends to see if I can see patterns. And so for one of the things we've been working on lately is a lot of our deep grade aquifer systems are channelized gravels. Chances are you don't have enough boreholes to delineate that, so what are the groundwater levels telling us? And here I'm along the Markham, the bottom. I'm over here, where from Stouffville trending southwest, we think we have a Thorncliffe channel. And I'm looking at water levels out in this area. So for the shallow till plain, I'm looking at a rise up until 2010 and then a gradual decline. And these are centimeters. But then when I get into the deep system, it's a bit of a different story. And we had a large event of pumping related to sewers, and that led to a trend of drawdown that emanated in a northeast southwest fashion. So basically I'm looking at where do I see this pattern, what does it tell me about the channel, and we're thinking these channels are like a channel esker or subaqueous fan type system. So theoretically under Toronto, I'm fanning out this channel. The next one of Rick Gerber with a crayon and a light table is looking at another channel we looked at quite a bit, and that's the Yonge Street Aquifer. Again, channelized gravel that we think at the south end fans out. So I'm just trying to see what's the response in that fanned out section. And it's all aimed at aquifer mapping. And you can see we've got some trends like when the pumping dramatically decreased along the Yonge Street Aquifer. But when I get out, say, to the west more around Nobleton, I'm starting to see some trends that kind of started a little bit before the big changes in pumping along that Yonge Street Aquifer. So I guess perhaps another great addition to this tool, and I'm not saying this is definitive because it has the same pattern, therefore it is. It's just pushing you to then go and check deeper into certain areas. And then we're extending this analysis beyond, well, it can easily extend beyond groundwater level data. Here, streamflow data, the GAM is a bit lost in the streamflow on the bottom. This white line is the GAM for the groundwater levels here. These density plots, so in blue, this is when, this peak is when most of the seasonal highs occur. And the red is when most of the seasonal lows occur. So this is October, and you can see for local stream flow, that peak, as expected, but not always, is earlier in the summer. And the highs, again, kind of correlate to spring, let's call it April. So there's ways that we're expanding this to other data sets. Plus, we need to bring in, trying to pull out what's natural and what's anthropogenic from that. And that would be overlaying climate indicators. Could be precip, could be soil moisture, could be a lot of different things. And then to end, there's a paper that came out recently that you may or may not know about, just Sechko et al., and it was in Nature. I think it was the 24th of January. And they took groundwater levels from all around the world. And did Thiel-Sen regression slopes on them. And their game was to try not to pull their hair out, but apparently they did, but to try and figure out just look at evidence of, do we have areas in the world that have huge drawdowns? And are these patterns extending for decades? And the answer is yes. And most of those places are in dry areas with extensive cropland or extensive agriculture, which is to be expected. But they did take the Provincial Groundwater Monitoring Network data. They downloaded it in 2021, and they do have estimates of rise or fall in groundwater levels. And from those data, and basically what they concluded for the Oak Ridges Marine Aquifer was, and they talked about 2000 to 2022, but this would be what, early 2000s when the PGMN started, and 2021 when they downloaded the data. And for the most part, the median change in the Oak Ridges Marine Aquifer system was a rise, that negative number is a rise of about 5 centimeters. Okay, so overall, that was the overall trend. This next picture is, if you sit back and look at it long enough, basically on the right is the Jusechko et al. Data, and all those filled in triangles that are pointing up, that's where they saw a rise over the period of record. On the left, I'm showing our 10-year, the last 10-year trend, and there's significant differences. So again, I'm just filling in the triangles that are showing an upward trend, but there's a lot of red, which are areas where we're declining. Okay, so I guess this is the key takeaway from this is, when you're looking for trends, you've really got to watch the time frame that you look at, because our changes, like I said, aren't monotonic. There's a lot of non-monotonic behavior, and what, you know, a lot of these hydrographs that overall give a teal sand slope of an increasing groundwater level, the hydrograph is doubled back on itself. It's non-monotonic, so you have to be careful. But in the grand scheme of their exercise, it worked. So I invite you, we've got a lot of this available on our website, and you can go, we have data snapshots when we have large data sets that don't work well in the GIS mapping environment, and we call them data snapshots, and this one's called Groundwater Level Variability, where you can get at the output from all of these almost 700 wells. And I invite you to look at it, because that would provide some help in looking at all this stuff. And I guess I'll end with thank you to all the people that and agencies that collect data. To me, that's the key. Whenever we have our next provincial funding cuts, I want to help try and make a case for, please don't cut our monitoring networks. Anyway, thanks for your time.